Okay, I think we are on time now, and I see most people return. So let's start the new session. So our first speaker in this afternoon's session is Andy Strominger, and he will give us a Blackboard talk on W1 plus infinity and celestial sphere. Please, Andy, go ahead.
Okay, so first of all, apologies. I'm actually, for obvious reasons, very interested in Amplitudes, the Amplitudes program these days, and I've been at another conference all week, and apologies for shooting it for my own talk without being here. The subject I've been working on, mostly celestial holography, celestial amplitudes. It's become, there's a lot of different parts of it. I'm going to actually, today, I'm not going to give a review thing. I'm going to just give a rather narrowly, but hopefully self-contained talk about something I'm particularly excited about. And it's this recent paper, 2105.346, W1 infinity in the celestial sphere, which jumps off from a previous paper with Alfredo Guevara, Mina Himwich, and Monica Pate. And even though I'm going to give a narrowly focused talk, I certainly welcome questions of any type. So the basic idea in the celestial holography program is you take the S matrix, which is the basic thing that we use to describe physics in flat space, and you rewrite it as a correlation function on the celestial sphere that lives at null infinity with various kinds of operator insertions, replacing incoming and outgoing particles. And the basic formula that describes how this is done is here. A primary reason for doing this is that the Lorentz invariance, SL2C, of Minkowski space becomes a conformal group of the celestial sphere. And moreover, that gives you the global conformal symmetry. And moreover, in quantum gravity, the subleading soft graviton theorem promises you that these things, this collection of objects here, which we want to understand as some kind of two-dimensional conformal field theory, actually transform under the full local two-dimensional conformal group when gravity is included. That requires gravity. And the basic objects on the right here, let me put them over here. We label these insertions by whatever quantum numbers they have. And also we have to have an ingoing and an outgoing label. We label them by their conformal weight delta. I guess probably also should talk about their spin. I'm not going to write everything out here. We have an amplitude which depends on, if we know the spin for n particles, which has 3 numbers for each particle, and that is equal to a simple, for massless particles, a simple Mellin transform of the usual momentum space amplitudes, where omega here, we're doing a Mellin transform over the total, over the energy, and where this variable z, z1 is related to p1 by the usual map, z is equal to p, or zk is equal to pk1 plus I pk2 over pk0 minus pk3. So z is the point on the celestial sphere where a particle of momentum p exits. Now, this is a bottom-up approach. We're not postulating any fundamental new physics here. We are trying to understand the real world, properties of the real world through this reformulation. But it has all kinds of inputs and lots of the ideas and ways of putting things together. We borrowed heavily both from the Amplitudes program and from string theory. And one of the goals of the program is to answer the question, what are the non-trivial symmetries of nature? So, 100 years ago, the answer to that question might have been symmetries or conservation laws. The conservation laws would be conservation of energy. There would be energy, momentum, charge, a few things. But now we know that in gravity and gauge theory, there are infinitely many conserved quantities. But amazingly, even though we know all the laws of general relativity and the standard model, we don't know what all the symmetries are what are all the symmetries of the S matrix of general relativity plus the standard model to the level of precision that we can compute it. And when I say symmetries, I mean non-trivial symmetries. I don't mean like redundancies in a description, such as gauge transformations with compact support that do nothing to the scattering amplitude. And this question is, so what are the symmetries? And during this talk, I will clarify how we're thinking about this question. There are a lot of different ways to think about it. And I left my eraser over here. And of course, that's interesting in its own right. But another goal here is to understand holography for flat space. And indeed, in ADS holography, the discovery that there was a set of string compactifications and a set of field theories that had the same symmetries was step 0 in identifying the holographic duality. Here, we haven't even completed step 0, and indeed, step 0 is far richer than it was in the ADS CFT context, and so we're trying to complete step 0. Okay, that is the end of my general comments, and now I'm going to plunge into some stuff. But if anybody has a general question, feel free to ask. Okay, so now I'm going to write down a formula, which was some amount of work to derive. But I'm just going to write down the formula and tell you what each term in it means without deriving it. And the formula is for the operator product expansion of, so here's my celestial sphere. And let's suppose I have two operators which create and annihilate two positive helicity gluons, or create. So they could be either an incoming or an outgoing positive helicity gluon, and I'm going to bring them near each other. And so the formula is O plus A, so here's the operator insertion, O plus A delta 1 of O plus A delta 1 of Z1, Z bar 1, O plus B delta 2 of Z2, Z bar 2 goes like 1 over Z1, 2. Of course, the gauge coupling constant, there's a minus I, F, A, B, C, O plus C, delta 1 plus delta 2 minus 1 of Z2, Z bar 2. And then there's a constant here, which is the Euler beta function, beta of delta 1 minus 1, delta 2 minus 1, where I remind you that beta of xy is equal to gamma of x, gamma of y over gamma of x plus y. So what does this formula say? Well, it's a statement about what happens when you take a scattering amplitude and you have two particles which are either entering or exiting at nearly the same point, at nearly the same angle in the celestial sphere. And this kind of thing has been studied for decades in quantum field theory. It's called the collinear expansion. And there's subjects with a whole subject with all kinds of properties of the, it's important in accelerator physics and also, and so you have to take those formulas. So how was this formula derived? Well, there's several different papers deriving it. The first one was Fotopoulos, Stieberger, and Taylor, where they simply brute force took the formulas for the collinear expansion and did a Mellin transform on them. Then I wrote a paper with Pate and Reclario showing that actually you don't have to do any work. You can just, the symmetries of the celestial sphere, uniquely fix them. And then there was an even simpler derivation of that just a few days ago by Himwich and of this formula by Himwich and Pate. So this is a very universal formula. And just to mention one really interesting feature of them, translation invariance, the price for going on the celestial sphere and working in a conformal basis is that translations, the action of a space-time ordinary translation becomes a little bit obscure. And what it does is it shifts the conformal weight of the delta of the incoming particle. And so you get recursion relations for these operator product coefficients, and they turn out to uniquely fix them. Now, this here, since I have a positive helicity gluon, these things have H bar, the left and right and left conformal weights, which would be delta 1 plus 1 over 2, delta 1. Let me write this formula over here where I don't have to erase it. H bar is equal to delta 1 plus 1 over 2, or delta plus 1 over 2, delta minus 1 over 2. So that the difference is 1, and that corresponds to the fact that they have spin 1. When we do gravity in a moment, H minus H bar will be 2. Okay, some comments about this formula. First of all, it only makes sense in theories with massless gluons. because it's about what happens out at infinity. So it doesn't actually apply to the real world, but similar formulas actually do apply to QED. Similar formulas apply to gravity. I'm just using this as a model. And of course, it would be true, for example, in n=4 Yang-Mills, where there are massless gluons. As I said, there's a similar formula in gravity. And a further, more technical point is that I'm going to take I'm going to treat Z and Z bar as independent. So I've taken Z1 to Z2 while holding the Z bars fixed. And that means that SL2C becomes SL2 right times SL2 left. And also, interestingly enough, another paper we wrote, the celestial sphere actually turns into a Lorentzian torus when you do this. Okay, and finally, I am going to consider, I'm only going to consider positive helicity gluons, not because negative helicity gluons aren't interesting, but just because it becomes a more complex structure and we don't understand it. And this can also be understood. The formulas, it turns out that in the MHV sector, that the negative helicity symmetries become trivial, and you can also understand the formulas I write as being exact in the MHV sector. And this point of view was espoused by Banerjee, Ghosh, and Paul, who have written a series of beautiful papers on things closely related to what I'm talking about today. Now, I'm mostly going to also, the formulas, everything is going to be tree level, but the soft theorems, the leading soft theorems are known to have been proven long ago to have no corrections in a quantum theory. The subleading soft theorem have limited corrections that come from some short list of higher dimension operators. And so we anticipate that this can be extended to the full. Our methodology doesn't preclude us from going on to the full, to the exact theory. Okay. Now, one thing you'll immediately notice about this formula is the striking fact that the operator product expansion has a pole when delta 1 or delta 2 are an integer less than or equal to 1. And the structure of these poles is what the whole talk is about, and it turns out to be an incredibly rich structure. So of course that means that the OPE becomes infinite, but we can take the residue and we can define an operator RA, and I'm going to put a 1 here for reasons which will become apparent shortly, is equal to the limit as delta 1 goes to 1 of delta 1 minus 1 O plus A delta 1 of Z and Z bar. And this operator, no, sorry, 1 over delta 1 minus 1. This operator, so I'm basically taking the residue. This operator doesn't, it looks like it should, no, I had it right the first time. I got it wrong in my notes. Delta 1 minus 1. This operator looks like it should be 0 and decoupled from the theory, but it doesn't. It has a pole because of this pole in the operator product expansion. So it has non-zero operator products with generic conformal primaries. And indeed, one finds that RA1 of Z with O plus B of delta of Z1, Z2, Z bar 2 goes like minus I FABC over Z1, 2, O plus C of Z2, Z bar 2 plus dot, dot, dot. This, of course, also has plus dot, dot, dot. And the corrections are both subleading in powers of Z and okay, so what is this thing? First of all, why did I get to say that this depends only on Z? Well, we can see from this formula that it's a dimension 1, 0 operator. And conformal symmetry tells us that 1, 0 operators can't depend on Z bar. It's not consistent. And in fact, you can show that this is the only term, but you can also just see it by direct calculation. This is the only term that contributes, because when you multiply by the plus dot, 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 doesn't have poles in it. So this is the only term that is there. And of course, the way that it was originally discovered is that this can actually be derived from the soft gluon theorem. So, but an important subtlety here is that it's not energetically soft. Once we work on the celestial sphere, we don't talk about energy. Nothing is in an energy eigenstate. They're in boost eigenstates. That's what these conformal primaries are. They're in eigenstates of boost. And so it's not energetically soft, it's conformally soft in the sense of that it's going to an integer weight operator in a conformal field theory. So this is sort of the celestial image of the energetic soft theorem. And indeed, one can understand, once you have a holomorphic current, we can insert this operator and we can consider an integral over S matrix elements where we insert this RA of Z and we integrate it around a contour. And then we can deform that contour and we get various Ward identities. And those Ward identities can either be interpreted as the soft photon theorem, or they can be interpreted, and I'm going too slow, or they can be interpreted as they can interpret it as the infinite number of asymptotic symmetries. Now, there are other poles. What about the rest of the poles? Well, in the rest of the poles, you no longer have 1, 0. So we can't expand it. We can't do exactly what we did. But we can do something similar. Let me just write out what the formula is for the rest of the pole. Well, let me just write down the subleading guy. So the subleading soft photon, we take the limit as delta goes to 0 of now delta times O plus A delta. And we define that as square root of Z RA minus a half of Z plus 1 over square root of Z bar RA plus a half of Z. Now, what happens here is that the left conformal weight becomes minus a half. And we're not too familiar with that kind of thing, but there are finite dimensional representations with conformal weight minus a half. So we don't have a whole arbitrary Z bar dependence. We just have a doublet under the SL2 left. So we have a doublet of subleading soft currents. And right, we have a doublet of subleading soft currents. And it was already known that when you transcribe, it was already known that there were two subleading soft photon theorems. Okay, so going on, we get a whole tower of fields, going down all the poles, we get a whole tower of fields, RA, K, comma, N of Z, where now N runs from K minus 1, K minus 1 over 2, less than or equal to N, less than or equal to 1 minus K over 2. K equals 1, comma 0, comma minus 1, down to minus infinity. We get a whole tower of fields like this. And using this operator product expansion, we can actually write their commutators. They're two-dimensional commutators, but by which I mean what you get when you take a contour integral of one around the other. And the formula that you get for the infinite tower of soft currents, each in a finite SL2R left multiplet, obeys 2D commutators. Now, I emphasize again that these things each depend on Z, R, L, B, M. They're each a Katz-Moody current on the celestial sphere is minus I, F, A, B, C. And then something rather complicated, and it all follows from this operator product expansion, 1 minus K over 2 plus 1 minus L over 2 plus N plus M over 1 minus K over 2 plus N. Now, our paper is full of long formulas like this, and I promise this is the only one I'm going to write, times N goes to minus N, M goes to minus M, times R RK plus L minus 1, comma C, N plus M. This depends on Z, this depends on Z. And we showed that this obeys the, this is what you get directly from the OPE, and this obeys the Jacobi identity, and so on. Okay, so this is an infinite, this is the algebra of the infinite tower. So there have been a number of papers, Hamada and Shu, Guevara, Zhang and Ling, talking about the fact that there are infinite towers of soft theorems. And nobody knew quite what to make of them, how they're organized, whether they have a closed algebra, or whether you just keep getting more and more. And what we're seeing is happening here is we wrote down the algebra. It has the property that the leading and the subleading soft theorem generate the whole algebra. So you don't get new constraints for gauge theory. You don't get new constraints on the scattering beyond the first two soft theorems, but there is an infinite tower of soft theorems with an algebra, albeit at this point, a very complicated looking algebra. Okay, so now, and we also did the same thing for gravity and for gravity coupled to gluons. Okay, so now in gravity, the OPE looks a little different. Some of the numbers are shifted. Again, it involves an Euler beta function, and you get a very similar structure. And you get something, you get a tower of fields which have conformal weights H bar equals K plus 2 over 2, K minus 2 over 2, where now K runs from 2 down to minus infinity. And we get a infinite set of currents, HNK of Z, where H the leading one, actually H1 of, let me not talk about H2 of Z, I'll come back to that if somebody asks me a question. H1 of Z is basically the super translation current, generates space-time translations, certain modes of it. And then we have H0n of Z, which is the super related to super rotations in a somewhat subtle way. Shadow generates super rotation. And then we have an H minus 1, which is related to the sub-leading soft graviton symmetry. And it keeps going. We also computed their algebra, and it was even more complicated. And then in my recent paper, I found that all of this this structure which followed from the OPEs dramatically simplifies if you define WNP of Z is equal to gamma of P minus N, gamma of P plus N, H N minus 2P plus 4. Okay, so if you do this, the algebra for the H's, which would have taken a substantial fraction of my talk to write down, collapses down to WNP, WNQ, these are currents again, is M, Q minus 1, minus N, P minus 1, WM plus N, P plus Q minus 2, where now P runs 1 over positive integers. And 1 minus p is less than or equal to m, less than or equal to p minus 1. Okay, so this is a very simple algebra. So if we just look at the algebra up there and ignore the restrictions and ignore the restrictions on the range of m, and ignore the dependence on z, this is known as the it's called little w 1 plus infinity. The fact that this is restricted means that it's something called the wedge algebra of W1 plus infinity. And by the way, I enjoyed some lecture notes by Chris Pope on all this. This was a very active subject in the early 90s, and actually even it keeps coming back up. And the fact that it's a current algebra means that it's the Kac-Moody algebra of the wedge algebra of W1 plus infinity. That's what we have here. Exactly this algebra has appeared repeatedly in the literature. In the early 90s, Klebanov and Polykov found that the discrete states of C equals 1 string theory generate exactly this Kac-Moody algebra of the wedge algebra of W1 plus infinity. And in a quantum theory, when you have an algebra, the states are also acted on by the enveloping algebra of whatever the operators are, because you can always have products of the generators acting on the states. And the enveloping algebra of the Kac-Moody algebra of the wedge algebra of W1 plus infinity contains W1 plus infinity. And so generally one just says this has a W1 plus infinity symmetry. But if we want to be more precise, it's this other thing, which is actually bigger than and contains W1 plus infinity. Now, if we look, for example, if we look, for example, at compared to our old H's, which if we define Lm equals Wm2, where now m would be 0 plus or minus 1, we find that these things generate, for example, an SL2R. And indeed, SL2R is the wedge algebra of W1. It's a wedge algebra of Virasoro, and similarly, this restriction is like restricting Virasoro to in this way. Now,
Andy, just to say that there is 5 more minutes.
5 more minutes, great. So 4 good things have happened. We had a very complicated algebra. The symmetry of nature, which this is, that you get by looking at all the soft theorems, the positive velocity soft theorem, looked very complicated, at least it closed. But now we found that it simplifies to one of the most studied higher spin two-dimensional algebras known. Secondly, and rather surprisingly, in the old basis, in the old organization of all these currents, of all these soft currents that generate the symmetries, there were negative weights appearing all over the place. Most of the soft currents had mostly negative H left and H right. That's a different SL2. There are a number of SL2s floating around. And organized in this way, we see everything is appearing with a nice positive weights. And so that looks good. And moreover, this transformation here is essentially what's called a light transform. And there's it's like a shadow operation or two-dimensional conformal field theory, but you only do it on one side. And so there was a recent beautiful paper by Sharma in which he argued that celestial physics, it's good to do everything in the light transform basis. And that's essentially equivalent to the half, going to the half, or the ambidextrous, the ambidextrous twistor formulation. So when you do that, there's when you go to this basis, some of the scattering amplitudes in the ordinary non-light transform basis had singularities in them. And this, in the light transform basis, all those contact term singularities, they didn't violate any principle, but one had to deal with distributional scattering amplitudes. Of course, this one does in momentum space, but here, going from momentum space to conformal basis got rid of some, but not all of the delta functions. And in this basis, we seem to be rid of all the delta functions. And moreover, it's closely related to things that have already been discussed and ties this subject in with twistor space. Let me now mention that there's another transformation on the gluon operators, a similar looking one. And they turn out to all transform in a positive way, irreducible representation of this W algebra. And there's a very simple closed algebra for all three of them, which can be found in my paper. So three quick closing comments. Maybe I'll just make two. So we need to go to the full quantum theory. And it's known that the little W algebra, there are two-dimensional systems which have that symmetry in the classical limit, but then when you quantize the theory, it gets deformed to what's called capital W. And capital W is way more complicated. There seems to be a two-parameter family of deformations. And capital W is way more complicated than little w. It's known that it exists as an algebra. The recursion relations for the structure constants, but it certainly exists. You can realize things with capital W algebra with free fermions or free bosons in 2 dimensions for some special values of these parameters. But the closed form expression for the structure constants is hard to get. So the natural speculation here, this is a tree level analysis, is that when we go to the full quantum theory, that the corrections that we know exist to the subleading soft theorem will deform this to the capital W algebra. That's a hope that I don't have that much evidence for, but it's the nicest, would be the nicest continuation of this story. The other thing I'd like to say is that this W1 plus infinity is well known to appear in the study of self-dual gravity and self-dual gravity in 2,2 signature, which I'm exactly what I'm working on here. Self-dual gravity is a subset in 2,2 signature, is more or less what is studied in the twistor program. The idea which we're pursuing now with the holographic duality is that we know that self-dual gravity in the bulk it's already been said in many places going back to the 60s, that it has this W infinity symmetry. And now we're seeing the W infinity symmetry on the celestial sphere. And so the natural hope, speculation, is that we can find a holographic duality of holographic dual to self W gravity, which is some kind of W1 plus infinity conformal field theory living on the celestial sphere. So let me stop there. Maybe I'm a few minutes over, sorry.
Okay, yeah, thank you very much. No, it's just on time, and thank you very much for this inspiring talk. Let's all unmute and thank Andy for this talk. So at this point, let's open discussion. So I don't see hands up yet, so please. Okay, Enrico.
Hey, Andy, thanks. Thanks for this great talk. So just in relation to the quantum corrections to the soft theorems and this relation to your big W algebra, so is your idea or your conjecture that all orders corrections to the soft theorem give you this capital W algebra? Or like from the amplitudes point of view, we can compute it order by order in H-bar, like loop order. So do you think already from the one loop correction to the soft theorem, you get this big capital W algebra? Or do you need all orders corrections to the soft theorem to end up at the capital W algebra?
Well, I don't want to use the word think. I'd rather use the word speculate. But what I would hope happens, so that the corrections to the subleading soft theorem are very limited. And I think that it's some limited set of operators. And I think that they would drive corrections to all the subleading soft theorems. But
what about the leading one gets corrections to all orders in at least in gauge theory.
Okay, the leading one gets corrections to all orders in gauge theory, and gauge theory is a gauge theory is a confusing example for thinking about that, because in gauge theory, what the whole thing, if you really think about what the full non-perturbative structure is, there isn't one, because it gets confined, and so there aren't any asymptotic gluons. So you don't really have this structure.
You can consider n equals 4, where there is no confinement. And then...
Right, so n equals 4 is a good thing to consider.
But that has also, all orders corrections to the leading, and I guess also subleading soft theorems.
Well, right. So there was so there's a question there about a lot of interesting questions here, and I'm not gonna. But in this story, you do the Mellon transform first, and when I guess it was Byrne, Knoll, and somebody else wrote a paper maybe 5 years ago about corrections in n equals 4 to subleading soft theorems, and when they do that, they take there's a question of the order of limits. And the question of whether you want to take the amplitude of the now, first of all, they were talking about soft theorems, not conformally soft theorems, but they're related. So in the soft theorem, they took the infrared cutoff to 0 before they took the weight of the soft particle to 0. And if you do it the other way around, which Cacciazzo and somebody else wrote a paper on, then there are no corrections to the
it has to do with how you implement dim reg in the soft limit,
and
right?
the right way to do it here is the other way around. And more generally, it's the other way around, because what Byrne and friends showed was that there's a correction to a formula, both sides of which are exactly 0. And the reason that both sides are exactly 0 is that they were computing exclusive scattering amplitudes where the infrared divergences exponentiate and set everything to 0. So there's no, now if you're scattering coherent states, dressed states for which there are no infrared divergences, then you don't need an infrared cutoff, and you can take the soft particle all the way to 0. But anyway, here in this construction, in the story of celestial amplitudes, all their good properties are only happen if I start doing the Mellin transform and I put a cutoff on that. Everything is nothing works. Now, I'm not. This is a very interesting and important subject. There are a lot of things I don't understand about it, but I don't think there's an inconsistency there.
Okay, yeah, we are running short on time. Let us have one more quick question. Lorenzo, is this, can it be a quick one? Please, Lorenzo.
Sorry, I was muted. Can you hear me now?
Yes.
Well, mine was actually more like a short comment to Enrico's question. And I was simply going to say that as far as the leading soft theorem is concerned, I'm now talking about loop corrections and infrared divergences and such. Then what happens is that all these loop corrections organize themselves into a prefactor. So the conformal structure on the celestial sphere is left essentially untouched, and there is like a normalization which ends up containing all the regulator and scale dependence. So it's a bit of a, I mean, this in one way to put it, this puts a big constraint, which it was found years ago that QCD already, or gauge theories already satisfied this constraint. But all of the loop corrections organize themselves into a prefactor, which is actually a very well-known object in QCD. It's like a scale average of the Regge trajectory. That was just a comment.
Okay. Very good. So thank you very much. Let us close the discussion now. So thank you very much, Andy. Let us clap.